For this video, I'm going to talk about these first two bullet points here. That's our goal for this video. So we're going to talk about the peptide bond and how that influences the three-dimensional shape of proteins and peptides. And so there's a structural hierarchy with proteins that we will get into and how that influences the function of these proteins. So that's our goal here. So proteins are just a linear sequence of the 20 natural amino acids. And depending on that order of those amino acids, those amino acids are going to fold and twist into a three-dimensional shape that's very unique to its function. When proteins fold into their, I want to call it like their normal three-dimensional shape, which really that's not the right way of saying it. It's actually the native fold. So you have a protein sequence, and that primary protein sequence encodes for how that protein is going to fold, which is another way of what does its three-dimensional shape look like. Okay, and when you get that three-dimensional shape, we call that the native fold of the protein. And when you have a protein in its native fold, that's where evolution and nature's come up with the, hey, if the protein looks like this, it will have X function. And so in order for proteins to behave the way that they were designed to, they have to be in their native fold and in their proper three-dimensional shape. And so shape is everything to protein function. It's critical, super, super critical. Now, this last point right here is that it takes energy in order for this protein to fold into its three-dimensional shape. So for example, you could have a repeating unit of amino acids, okay? And I'll just represent that peptide or protein like this. Here's our N-terminus, and here's our C-terminus, okay, like that. So that's, when you just look at the amino acid sequence, that's called the primary sequence. And that primary sequence, that right there is an unfolded protein or peptide, because there's no three-dimensional shape. But when that protein wants to fold, it can fold in many ways. One very common is a alpha helix. So we could have it fold like that, and we would have, let's put our N-terminus here and our C-terminus there. Okay. So what we have here is, in this linear state, okay, there's more disorder, and that's thermodynamically favorable, right? But then when you look at this structure here, this piece folded into an alpha helix, and there's more order. So there's an entropic cost for this process to happen. Okay? But if this is the protein of interest, this version right here, it doesn't perform its biological function. It will only perform its biological function when it's in its helical state or its folded state. Okay? So how do proteins fold? Okay? There's a lot of interactions that you're so familiar with, that you've already heard of many, many times in general chemistry and organic chemistry. And these terms, you'll see here, hydrogen bonding, London dispersion forces, electrostatic interactions. Those are interactions that you've learned in general chemistry and organic chemistry. A more new concept that you've learned in biochemistry is the hydrophobic effect. So we've discussed that in great detail in other videos. You've learned about hydrogen bonding since like your first days in chemistry. London dispersion factors or dispersion forces, Electrostatic interactions, you've heard about that from general chemistry as well. But I want to put a little context to that point right there, just so you can see like what's going on here. And we will talk about this one a whole lot more when I go through what alpha helices look like and why they fold the way they do. But this electrostatic interaction, let's say you have a peptide or protein. We have an N-terminus here. And then we just have a linear chain. Okay. We can draw our like that. Okay. So this electrostatic interaction here. What if this linear sequence of amino acids encodes for a shape of a loop? Something that looks like this. Okay, we have a loop. What can help this loop to form and stay in a loop when it folds? So right there, electrostatic interactions. Okay, and in in biochemistry, we call those salt bridges. A salt bridge is just an ionic interaction. We could have a side chain of an amino acid that is positively charged, and then a side chain of an amino acid, another one, negatively charged. And you see there, we have an ionic interaction right there. And represent it right there. And so those two different charges kind of help hold that peptide in that loop shape. So that's an ionic interaction right there. Okay? Or we call that in biochemistry a salt bridge. And so it takes many, many of all these interactions to help proteins fold in their native fold. Okay? So it's not just one or the other. It's really a combination of all of this as to why proteins fold the way that they do. Okay? And we're going to pay attention as I go through examples. I'm going to highlight these interactions in these three-dimensional shapes or these folds so you can kind of relate and correlate them. So the first thing, I've already talked about it and referred to it here, is the 4 levels of protein structure. The first level is the primary structure. And the primary structure is just the sequence of the protein. It just lists out all the amino acids. And it's so cool, and we'll talk more about this, that this primary structure, just knowing the sequence, is going to encode for what its three-dimensional shape is going to look like. And so here we have a primary structure, and then we go to a secondary structure. Now a secondary structure here, in this particular example, is a alpha helix. But there's other different types of secondary structure. There's a coil. There's a beta sheet, beta loops, beta turns, all things like that I'll show you what I'm talking about. But the main idea is that the linear sequence of the amino acids encode, say, hey, we're going to look like this. Okay? And that's a secondary structure. Helices and beta sheets. We'll keep it at that for right now. But then you could have a protein, okay, that's really, 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 really long. There's our N-terminus and our C-terminus. Okay? And we could have, let's say, a segment of this massive protein, let's say 300 amino acids long. We could have a small section right there. That could be an alpha helix. And then you could have another section We'll see what this does for us. Okay, another section right there we could call a beta sheet. And then we could have other secondary structures all throughout this protein. So with all these different types of secondary structures in this protein, it can then fold further into a tertiary structure where that whole peptide or that whole protein that's composed of secondary structures, they can all then mush together into its native fold. And that's our tertiary structure. So when you look at this tertiary structure, in this particular example, what you see is one alpha helix right there, and then another right there, and then another there, and so forth. And so in this example, there's like 3 or 4 alpha helices that have all folded in to form more a globular looking protein. Globular meaning that it's kind of like spherical. Okay. And then you see that this tertiary structure right here, what happens to it when we go to the quaternary structure? It plops right over here. Okay. But what you see here, we have repeating units here. We have this unit, protein of tertiary structure, then another protein that looks exactly the same. It's just oriented in a different space. And so what's happening is in a quaternary structure, we're taking oftentimes many proteins. Let's just, in this example, 4 of these units right here. And these units right here they have their tertiary structure. And then we just put them together by intermolecular interactions to form a quaternary structure. And each one of these, from secondary, tertiary to quaternary, these peptides and proteins have to have that native fold in order to function. You mess up the helix or the tertiary structure in any way, the protein will oftentimes just not function at all. But in a more worst case scenario, it could lead to death or some kind of disease. So understanding how proteins fold and why they fold the way that they do is a very important area of research and an important area to understand. Because when you go to and do a quick Google search and look at like the top 100 drugs that are on the market, you're going to find that there's a significant amount of protein drugs. 20, 30 years ago, there weren't so many. But as time progresses, we get more and more protein type drugs. And like I said now, this is like third or fourth time, they need to be folded. How do they fold? How can we keep them folded? And if we can answer those questions and figure that out, then we can make some really powerful protein therapeutics. So let's talk about the primary structure, bare bones, and really focus on this peptide bond right here and why that's so important. Okay. So I'm not going to read these bullet points to you. What happened? So every time I write there, it just shrinks on me, huh? Okay. So let's just go through show you a picture of what these bullet points are talking about, okay? So this first point right here, the structure of a protein is partially dictated by the properties of the peptide bond / the peptide sequence, okay? So if we come here, I have 2 pictures here. Where is the peptide bond? Okay, up top we have a skeletal structure and then we have a ball and stick model. Being able to identify the amide bond / peptide bond is critical. So this bond right here, that is the amide bond. Okay. There's our amide bond, which is also the peptide bond. So those go interchangeably. Okay? And what we have here is when we take a look at the ball and stick model, where's the amide bond? There's an amide bond right there. Where's another one? Right there, and so forth. Okay. And so as we trace our pen through the alpha carbon, the carbonyl carbon, the amide nitrogen, and all the way through, okay? Can't see that probably too well, but that green bond right there, that's called the peptide or protein backbone. That's the backbone. And then we see our R groups, which are the side chains. So we have the backbone, and the protein backbone is unique in the fact that when we take a look at the amide bond right here, or the peptide bond, what is the hybridization state of this carbon? What's the hybridization state of that nitrogen? Well, you know that there's a lone pair here on this nitrogen, and you can see that it can resonate. So when we take a look, what we've noticed is that the amide nitrogen right here is sp2 hybridized. That carbonyl right there, that carbonyl carbon is sp2 hybridized, and the oxygen is also considered sp2 hybridized. So these atoms right here are considered sp2 hybridized, but they're not quite, or no, let me take that back. They're sp2 hybridized, but they're pretty much planar. And that's what's being represented with that blue rectangle right there, is that those bonds right there are planar. And they're pretty much sp2 hybridized. Now there's some argument and debate. Are they really sp2 or is it more sp3? For the purposes of our class, we're just going to say that they're sp2 hybridized, because when we look at crystal structures, we see that this part right here is nice and planar, or relatively planar. Okay? So we have our amide bond, which is planar. And what also happens, okay, is that when I show you a model here, and let's take a step back about protein folding and kind of just wrap our minds around how complicated that can be. Okay? So here I just have some random molecule that I just put together. And you don't need to pay attention to what atom is which. It doesn't matter. The point is, the way I'm holding this molecule, it has a three-dimensional shape to it. And proteins fold in a native fold, but what are the odds of a protein folding in that particular way every single time? Because just look at the entropy associated with this. This bond right here could have an orientation like this, or like that, or like that, or like this. There's 360 degrees at which this bond could rotate. And why does it kind of more or less stay at that position? And then you could come and look at this bond right here. That has free rotation. And then you could look at every single bond here. It has free rotation, right? And so I think it's so amazing that when you take a much larger molecule like a protein with 300 amino acids, each of those bonds, or most of those bonds, have free rotation to form its quaternary and tertiary secondary structures. it's amazing that it just folds the way it's supposed to every single time. And what helps it fold? All those things that we just briefly discussed. The hydrophobic effect, hydrogen bonding, intermolecular interactions, things that you have seen time and time again. But one aspect now about the amide bond is because it has this double bond character right here, it prevents that peptide bond from having the free rotation that I just talked about. Okay? So that peptide backbone has become a little bit more rigidified. I don't know if that's even a word, but it's become more rigid. Okay? And so that helps also influence its protein folding, because now we've kind of limited the amount of free rotation around one of the bonds in a amino acid. Okay. Another thing right here, okay, trans conformation. In the peptide backbone here, you are going to form the trans bond, or the transamide bond. And the way that you want to look at that is, if I clean this up a little bit here, all right, we're paying attention to the amide bond right here. All right. And then we see, hey, this alpha right there and this alpha right there. Do you see how they're on opposite sides of that amide double bond? So that is trans. The amide bond in proteins and in peptides, 90%, or like, what was it? I think it's like 99%. I don't have the exact number, but really high. Okay? Amide bonds are in the trans conformation. Because if they're in the cis, then we start introducing things that break secondary structure. And it's just more sterics, and it's just a whole lot more difficult to have amide bonds in the trans conformation. We will find some examples, though, where that is the case. But you just need to remember the majority of our peptide bonds are going to be trans. Not always. I misspoke there. The majority of our peptide bonds are going to be trans. So protein conformation is influenced by what we call dihedral angles. And dihedral angles are simply looking at, in this particular example, the angles between this plane and this plane. All right? So what happens is this plane is going to be represented by my hand, okay? And then this plane is going to be represented by my other hand. Okay? And a dihedral angle is simply the relationship between those two planes. What is the angle between those planes? So if I go like this, okay, you see how my hands are eclipsed? But that's a dihedral angle. Or I could have it like this. There's a dihedral angle. What if I went in the opposite direction? Okay, do you see? I'm comparing the angle between those two planes. Okay? And you guys already know how to really look at dihedral angles when you go back to organic chemistry and you draw the Newman projections. And so a dihedral angle is going to be calculated by looking at 4 atoms. Always 4 atoms are the main ones that you're going to look at, and you're going to use the Newman projection to help figure out that dihedral angle. Now, these dihedral angles, there's 3 of them that you need to be aware of. Okay? The first one right here is the phi angle. And the phi angle is looking at the rotation around this bond right here. So what is that between? That is between the nitrogen and the alpha carbon. That's the phi bond. And then when we go to draw our Newman projection, it's going to be between 4 atoms. This guy, that guy, that guy, and that guy. So what's going to happen here is we're going to draw a Newman by taking our eyeball and looking down the phi bond, which is through the nitrogen, through the alpha carbon. And then we can draw that. We can draw the Newman to represent that dihedral angle. We have a second dihedral angle, okay? And that's called the psi. So we have, let's just write it out here. We have phi, okay? That is represented like this. There's our phi. And that's between looking at this bond, the nitrogen and the alpha carbon. If we change our color here, let's go green. And then we have a psi. It doesn't like green, huh? Black works. There. No. Psi. Okay, we have a psi angle, and that you can see is right here. And that's between the alpha carbon and the carbonyl carbon. That's the bond that we're looking at, the rotation, right there. And what 4 atoms are going to be involved when we want to draw our Newman? It's going to be this guy, that guy, that guy, and that guy. So when we want to draw our Newman, where are we going to put our eyeball? We can go right through like that. Okay, so that's our psi angle. And then there's another one that you need to be aware of, but we're not going to worry too much about calculating it, and that is the omega. Okay, the omega bond. Let's make sure we get this. Omega looks like more or less a W. Okay, there's our omega. And the omega bond is this one right here. Okay, that's our omega angle right there. And that one we don't care too terribly much about, because what bond is that? Okay, it's this one. It's our amide bond. And I've already discussed that, hey, peptide bonds are going to be trans from one another. So what would the dihedral angle be for almost every single amide bond? It's trans. So that has to be 180 degrees. And that doesn't change very much. It's the ones that change a lot are the phi and the psi bonds, because there is going to be free bond rotation. Okay? So if we want to look at it from this perspective here, where's our phi and psi bonds on this guy? Well, in order to do that, we have to expand it out a little bit. Let's draw our nitrogen here. Okay, something like that. So remember, our phi angle is between the nitrogen and the alpha carbon. So there's our phi right there. And then what is our psi angle? It's the carbonyl right here and the alpha carbon. So right here. So in those bonds right there, we do have free rotation. Well, we have more rotation than the omega bond, which is right there. Okay. And it's that angle, depending on the phi and psi angles or the dihedral angles, determines if we're going to have a helical structure or a beta sheet and all the other secondary structures that we're going to discuss. Okay, so this is really important, and I want to spend time on it. And so let's go through it. Okay. So I want to first take a look at, let's say, let's take a look at, let's do let me, also my trick here. How do I know what is the phi and the psi angles? How do I keep that straight in my head? Okay, and kind of the way I do it, phi kind of sounds like F, and psi, say S, so it's in alphabetical order. Or if you just know the Greek alphabet, phi comes before psi, alphabetical order. But when you read a peptide or protein sequence, you read it from N to C terminus, right? So what comes first when you read from N to C? You come up with this bond. And what does the Greek alphabet say? Phi comes before psi. And then what's the second one? The psi bond right there. That's second in the Greek alphabet, or psi, sorry. And then the next one, which is omega. And omega is the last letter in the Greek alphabet. So that's how I keep track of that. Like, what is the phi and psi angle? Well, I'm just like phi, F. That comes before psi. And that, I know it's really silly, but I have to do that in order to remember that. Okay? So let's take a moment here to just draw a Newman structure real quick, okay? Of this, let's look at the phi angle. So we've learned in organic chemistry, we are going to have a circle and a dot, all right? Now that dot, okay, that dot is the nitrogen atom. So if we come back here, the dot is the nitrogen atom. And then when we go through, what do we see? The back carbon is going to be the alpha carbon. So the big circle is the alpha carbon right there. Okay, and let's just draw something that looks like this. I'm going to draw it like this. Okay. And then we'll just draw the squiggle because we're not going to worry about what that's. Whoa. All right. Like that. Right? So let's correspond that real quick. The dot is the nitrogen, and the big circle is the alpha carbon. So let's come back here. Nitrogen. Okay, there's our nitrogen. There's our alpha carbon. What's attached to the alpha carbon? The carbonyl right there. And that's what you see right here. Okay, remember, this carbon right here is attached to the alpha, which is the circle. So that would have to be that carbon right there. And then what's directly attached to the nitrogen? This carbonyl right there. And you can see that one right here. Okay? So that's the nitrogen, that's the carbonyl, like that. So what we're looking at is, hey, the dihedral angle, which is from here to there. And when we look at that, hey, that's 180 degrees. That's the dihedral angle in that example, okay? What influences the dihedral angle? What am I omitting on this Newman here? I'm omitting the lone pairs, I'm omitting the hydrogens, I'm omitting the side chains. Those matter. Those help and influence the shape or the dihedral angle that we're going to experience. Okay, so let's just draw everything that we already have, redraw it. Like that. Okay, so on our nitrogen atom, right here, what's attached to it? There's a lone pair, and there is a hydrogen. So if we put that on there, we could have something that looks like this. There's our hydrogen, and there's our lone pair on our nitrogen atom. And then on the alpha carbon, represented by the big circle, we have a side chain. And a hydrogen, like that. Okay. And the R right there is our side chain. And depending on the side chain is going to determine the dihedral angle from here to there. Because some R groups are small in size, some are really large. And so the sterics of this side chain is going to influence the dihedral angle. Okay? So that's what the dihedral angle is about. That's how you look at it. And so the next thing that we want to talk about this slide right here, maybe just another way for you to visualize the phi and psi angles. So I've given you a zigzag structure right here so you can see that. And remember, if we wanted to draw our Newman, we would take our eyeball, go right through there, like so. And if you wanted your psi angle, you would go look at it like that. Okay. So I think that's all a review right there. Let me just double check my notes to make sure I'm not missing anything. Okay. Okay, so this bullet point right here, talking about certain phi and psi angles. Depending on those phi and psi angles, they can enhance hydrogen bonding. And remember, hydrogen bonding is one of those principles that will influence a protein's three-dimensional structure. Okay? So we'll talk about that when we take a closer look at alpha helices. Okay? But what I want to share with you right now is this Ramachandran plot. That's where you take a look at a phi and psi angles of the common secondary structures here. And so you see on the x-axis you have the phi, and on the y you have the psi. And there's only particular regions in this graph here that have secondary structures. So you see this part right there is the dihedral angles will give us alpha helices. So what do we want? So if you like our phi angle right here, what? Like negative 50-ish. And if you're around negative 50 right there, on the psi angle, if your amino acid has those dihedral angles, then there's a good chance that that amino acid is good for alpha helices. Whereas if you come up here to beta sheets, you see that those dihedral angles are drastically different than the alpha helix. So what's cool is there's certain amino acids that favor helices, certain amino acids that favor beta sheets, but it's a general term, okay? There's always going to be some sort of exceptions that we'll find, but generally speaking, if you want an alpha helix, you want those dihedral angles. And look at this. Smaller amount, we could even have a left-handed alpha helix, but it has those dihedral angles shown there. Okay, so a Ramachandran plot plots all those dihedral angles, and then it correlates, hey, let's look at all the crystal structures that we have of proteins, find their dihedral angles, and then what secondary structure is present. And then they plotted it. And so we have an idea now, like when you want to design a protein or a peptide, and you're like, hey, I want it to be alpha helical. You'd be like, oh, I need amino acids with dihedral angles around that. Okay? But here's the crazy thing. Those dihedral angles for that amino acid could be what the textbook says, but you could take that amino acid and then put it, oh, let's say with the textbook, that amino acid was next to serine and serine. But if you take that same amino acid and stick it in between, let's say, proline and alanine, the dihedral angle of that amino acid is going to fluctuate. It's not just a solid, strict one number. The dihedral angles of those amino acids are in a range, and what's next to it also influences those dihedral angles. Okay. Okay, we will first start off looking at what an alpha helix actually looks like. Then we'll go to the beta sheet. Okay, so alpha helix, we know looks something kind of like that. And a beta sheet kind of looks like this. But a random coil, which is basically saying it has no secondary structure, the lingo is it just looks like a random coil. I call it limp spaghetti. Okay? Just something that doesn't have secondary structure. It's just bleh. Okay? So there's a chart here that gives you some information on some ideal bonding or dihedral angles. And so here's like the propensity of these. So when I looked at the Ramachandran plot, we came up with those numbers right there. Okay. So we are going to focus a lot of attention on why alpha helices form the way they do, why beta sheets form the way they do. And it's all, I want you guys to make this connection, it's all going to come back to this. I'll be like, look at this hydrogen bond, look at this salt bridge, okay? And then always in the back of your mind, hydrophobic effect. How can we get rid of water? Things like that, okay? Okay, here's a picture here of our alpha helix. What we have is an imaginary rod in the middle, right, or a pole. And what happens is that we have the amino acids just spiraling up that rod. which is completely imaginary. So it's not attached to anything. It's just the proteins or the amino acids just go into an alpha helix. And so if you take a top-down view, this helix right here, you could look at it from the top looking down, and what do you see? It's kind of like a core. It's hollow in the middle there, and then the purple atoms are all the side chains. Do you see any purple atoms on the inside of the helix? No, they're all on the outside. Okay? And this right here is just another representation, but this right here is a helical wheel. Which is a very useful tool when looking at alpha helices. And we'll talk about the helical wheel a little bit more later. Okay, but the first thing that I want you guys to pay attention to here is these major numbers right here. Okay? So in a right-handed helix, it takes approximately 3.6 amino acids to start at some point in space and then wrap around to that same space just slightly above. So if I start my amino acid right here, how many amino acids does it take to get to this point as it wraps around that imaginary rod? And the amount of amino acids is 3.6. Okay. You will see later on that there's something called a 310. Alpha. Let's see. Let's skip that. We don't need to worry about that right now. So that's a key feature about alpha helices. Another key feature, what do you see here with those dashed blue bonds? Those are hydrogen bonds. Those hydrogen bonds are oriented in such a way as to help keep the protein in its helical shape. And so this nomenclature right here, N and N plus 4, is simply saying, hey, let's take a look at an amino acid. Look at this one where the arrow's drawn. And we'll just call that N. And then if you go plus 4 residues, 4 amino acids in the sequence, you're going to end up in a spot where there's a hydrogen bond right here. Okay? That hydrogen bond is in an N and an N plus 4 relationship. And so you can see that N plus 4 relationship all the way up or down our alpha helix right here. Okay? And it's those hydrogen bonds that are helping stabilize that alpha helix. Now, pay very close attention. If I asked you what atoms are involved in this hydrogen bond. So it's a good idea to be able to take a look at the structures and really translate them into what's happening here. So if we take a look, we have a blue atom right there. What's that? That is the nitrogen atom, okay, in the backbone. Yes, you can have nitrogens on side chains, but that's not what we're looking at. We're looking at the nitrogens in the backbone, and you have a hydrogen directly attached to that nitrogen, and then you can see that it is forming a bond here with that carbonyl. Right there. Okay, so we're forming a bond with that carbonyl oxygen and our hydrogen on the amide nitrogen. Let's see, is there anything else that I want to talk about here? Let's take a look here. Okay. So what I want to take a look at now is, let's talk a little bit about this helical wheel here. And what this helical wheel, well, you know, let's come back to this, okay? And let's understand this n plus n plus 4 a little bit better looking at the helical wheel. Let's do that. Okay. So here we have the helical wheel, and those dots all represent amino acids. And the gold ones here represent hydrophobic amino acids. Okay, so there's a color scheme to describe what type of amino acids we're looking at. So this isn't a nitrogen. This isn't like some gold molecule or anything, or atom or anything like that. It's just different types of amino acids. Okay. Here, on the other hand, the colors mean something. The blue is nitrogen, the grayish black is carbon, and so forth. Okay. So what I want you guys to pay attention to is I want to address this 4 plus n, or n plus 4. If I want to designate atom or amino acid 2 as n, where would the n plus 4 be? Well, that's n, so now all we have to do is count 4 amino acids. So 1, 2, 3, 4. So amino acid number 6 in our example would be the n plus 4. And do you see how the second amino acid, or the n amino acid, and n plus 4, do you see how they're on the same side or same face of the alpha helix? Since they're on the same face of the alpha helix, then you can envision these hydrogen bonds are oriented in such a way that they can, or the atoms are oriented in such a way that there can be hydrogen bonding taking place. Okay? So another cool feature about these helical wheels is that you can use them to design proteins or peptides. So for example, if you had an enzyme that you want to target, okay, let's represent it. Let's just go like something like this. And there's this little piece right here in the enzyme. Let's call that a hydrophobic pocket. And what we want is to design a alpha helix that's going to just come in there and bind perfectly to that hydrophobic pocket. So you can go to the helical wheel and design and make sure that, hey, on our helix right here, we have different faces. So this face right there in particular, all right? So let's say we want that particular face of your helix to bind into the hydrophobic pocket. In order for that to happen, do we want hydrophilic amino acids on this side? No. We want hydrophobic amino acids like valine and isoleucine. And if we can put those on that side, then that's influencing our protein design so that that side, the hydrophobic side, can interact with that hydrophobic pocket. And so helical wheels gives you a quick way to like, hey, where should we put what amino acids should we put at the n position? What should we put at the n plus 4 position, or the n plus 3, and so forth? And you can figure that out. But it's really important in helping you design your alpha helices for protein therapeutics in particular. Okay. Now, in the Ramachandran plot, it demonstrated that you can have a right-handed alpha helix and a left-handed helix. And there's using your right hand rule and whatnot with your hands to help figure out what type of helix you have, if it's right-handed or left. I'm not going to go over that in this video because of how the video works and the images are being, transposed and all that crazy stuff. We'll talk about this in class. Okay, here's some bit of information here about the helix. Okay, how big the hole is, how big the grooves are and whatnot. But what's interesting here is that the particular shape of an alpha helix is well designed to fit into the major groove of double-stranded DNA. And you will see a lot of proteins, we know of proteins binding to DNA. And so a lot of those proteins that bind DNA may have a alpha helix that does that. Okay. Talked about most of that. Okay. Now what I want to talk about with you is some more guiding principles as to what makes a helix stay helical and how we can design a very stable alpha helix. And when I use the word stable, think of it like this. If we have an alpha helix like this, and if we increase the temperature on the alpha helix and it stays alpha helical, then it's a very stable protein or a stable alpha helix. But if we have an alpha helix and we increase the temperature and then it goes to a random coil or limb spaghetti, then it's not very stable. So oftentimes protein chemists, when we talk about stability of proteins or peptides, we're talking about, is it keeping its native fold when you change a parameter like pH, temperature, the salt content, and things like that. Okay. So let's go through and figure out what are these guiding principles that make an alpha helix nice and stable. All right. The first thing that you have already seen is the hydrogen bonding network. Okay. And how does that hydrogen bonding work with? Or it's the N and the N+4. And it's between the amide nitrogen, or the hydrogen on the amide nitrogen, with the oxygen on the carbonyl. That's the first thing that stabilizes alpha helices. Okay? The next thing shown here is that the side chain of the amino acids influences if it can be helical or not. And that's shown right here in this data. So what we have here is a delta-delta G. Okay? So what that's doing is we have a protein and we look at alanine. Okay? And we compare the other 19 natural amino acids to the energy difference of alanine. Okay? And so that's why we have alanine compared to alanine is going to give us a delta-delta G of 0. Okay? So when you look at this data, smaller the numbers means that that particular amino acid has a propensity to form alpha helices. So alanine has 0. So that's a very good amino acid that you want to choose if you want to form an alpha helix. Arginine has a very small number. It's good to forming alpha helices. You see leucine and lysine, really, really good. Right? So the side chains of these amino acids are going to influence if they're going to have the correct dihedral angles in order to turn into that helical shape. And you can see which ones are not very good. Proline, okay? Greater than 4. Proline, you don't find in alpha helices very often. Because when you take a look at proline, the amide nitrogen, it's connected to the side chain. It's in a 5-membered ring. So that nitrogen atom, because it's connected to the side chain in a 5-membered ring, it doesn't rotate. the dihedral angles are not very good for alpha helices. There's not enough rotation for that to happen. Second, that nitrogen is the only secondary amide in the peptide backbone. And because it's a secondary amide, it doesn't have a hydrogen. So if we come look at the helix here, if we look at our amide right here, this is a primary amide, you see that it has a hydrogen atom right there that can hydrogen bond. But if that is part of proline, there's no hydrogen. And since there's no hydrogen on that amide nitrogen, that can't participate in hydrogen bonding in a helix. So proline, it just won't be found in alpha helices. Okay? Let's take a look at, do we have another amino acid that does not have a high propensity for alpha helices? Glycine. Now that's a head scratcher for a second, right? Because glycine has a hydrogen for a side chain. So it should have the most flexibility and rotation, right? But there lies in the problem. Because it has so much flexibility, it's not constrained to stay alpha helical. It'll be like, oh, as I turn alpha helical, it's going to be like, this doesn't feel very good, so I'm just going to keep rotating so I feel better. And so glycine, you find very few of those in alpha helices. They're just not, because of too much free rotation. Proline, due to constraints in rotation and the lack of the hydrogen on the amide nitrogen. Okay. So another thing that you need to be aware of with alpha helices, okay, is it comes back to sterics again. It can happen when you have a helix like this, and if you have a side chain that's really, really, really bulky, right next to another side chain that's really, really, really bulky, there's going to be some steric clash. And so you got to be aware of that. But I think really cool and a little bit more important is if you have an alpha helix like this, and if you put a side chain and put a positive right there, or a positively charged side chain, well, what if you stick one that's negatively charged? Do you see now how there's going to be this interaction here, this ionic interaction? And so if you have that ionic interaction on the side chains, those can help stabilize or keep the alpha helix helical. So I think that's pretty cool. Let's see here. What's another thing? Do you think this would be good? Having positively charged amino acids all in the same face? No, that's going to be repulsive. So this peptide is going to not want to stay helical because it has too many positive charges all on the same face. Okay, same thing if you put all negatives on one side. It influences the stability. Okay, so the side chains are really, really important in determining if we're going to have, if it's going to be helical or not. And so when you see values that are less than 1 on this chart, yeah, they have a high propensity to form alpha helices. Okay, there's some other features here that help influence a helix to stay helical. Okay, we talked about hydrogen bonding, how the side chains can influence that. Let's see, what's some other things that can influence this thing right here. What we find in an alpha helix is that there's going to be a net dipole of a negative charge on the C-terminus, and on the N-terminus, we're going to have a net charge of a positive charge. Okay? And so what happens is the charges in the middle, they're all going to like do the hydrogen bonding and be okay, but it's the ends that we need to worry about when it comes to a net dipole. And the reason why we have a net dipole is when we take a look at the resonance structures here. Okay. So look at that resonance structure here. What do we have here? Let's see. A negative charge there, and then the positive charge on the amide. Okay. And so when the molecule or the alpha helix is in its helical state, we're going to have the carbonyl oxygens, okay, that have a partial negative charge oriented. So we could say, hey, we're going to have a carbonyl that has a partial negative pointing that way. We'll have another one pointed that way. Okay, so there's going to be this partial negative in that direction to the C-terminus, whereas when we look at the N-terminus, we're going to have a net positive charge. So what you're seeing, here in this little ribbon, do you see how you have negative right there? And then you have what? Positive right there. Do you see that all the way up on the ribbon? We have negative charge there, positive charge there. And that's all because of the orientation of the amide backbone. The carbonyl is there, and then the nitrogen is up there. And we have the hydrogen there. So it's just the orientation of the amide backbone there. That gives us at the C-terminus a negative charge, and at the N-terminus a positive charge. So how do we help stabilize this? Well, the last, or in this case, the first amino acid on the N-terminus, it'd be a really good idea to have that first amino acid to be negatively, its side chain to be negatively charged to help stabilize that positive charge. And then on the C-terminus, you want that to be what? You want the C-terminus peptide to have a side chain that's positively charged. And that's going to help interact with that net dipole of a negative charge. And so that's going to help stabilize the dipole. All right? So I have gone through 5 or so reasons. I've given you probably more than 5 reasons as to what stabilizes a alpha helix. And so what I want you guys to be able to do is to talk about those reasons of what stabilizes an alpha helix and why they're important. But your textbook does a nice summary of those 5 reasons. I gave you more than the book actually gave, but that's okay. But if you want to summarize it and to see it in text form, then go to your textbook, and I'm looking at it right now. It just, in summary, 5 types of constraints that affect the alpha helix. And it lists them out in a list for you. Okay, so be aware of that. So the next secondary structure that we can discuss is beta sheets. And based off of the length of the video so far, this will be a great point to stop, and we will talk about alpha helices or beta sheets either in class or in another video.